All right. Let's have a look here. Okay, a couple things worth maybe reminding ourselves about. For one thing, piecewise functions, right? Does everybody understand if I look at something like this? Everybody get what that means? That's a piecewise function. Whenever you see that kind of notation where you have a function equal to, and then you've got this left bracket only, a left script bracket with a bunch of different functions to the right, that's essentially a list of the different behaviors that that function has, right? It's telling us that the function has the behavior, this square root function, the square root of 16 minus x squared, on the domain where x is greater than or equal to 0 and less than 4. When we get to 4, the function changes, shifts gears and goes to the new function f of x equals 4, right? On the interval where x is greater than or equal to 4 and less than 8. And then when we get to 8, it shifts up to that one value, the function equals y equals 8, right? So which one of those is it? Well, this is, if we, I think it's early in the year, maybe it's worth talking about like even that for a second. Is that a little blurry? Is that just my old eyes? A little blurry to me. So what if we've got something like this? F of x equals square root of 16 minus x squared. Or more simply, let's just call it y equals square root of 16 minus x squared. Does everybody recognize what that is? Maybe it's a little tough to see immediately, but what if I square both sides? What happens? If I square both sides, this is going to become a y squared, right? Get rid of the square root. Then if I add the x squared to the other side, I get x squared plus y squared equals 16. Or x squared plus y squared equals 4 squared. Now what's that? That's a circle centered on the origin with a radius of 4. Okay, so if I were to graph that, not that this is hugely important, but I just kind of, it's a good opportunity for a little review. Almost every problem is a good opportunity for some review if you look at it closely enough. So if I graph that circle, it just looks like that essentially, right? Well, I missed it a little bit, but you get a radius of 4, right? Okay, if I graph this guy, is it a complete circle? It's not. It's not. Where did we, this is only a semicircle, isn't it? Right? If I were to solve this equation for y, if I square root both sides, I would get the answer plus or minus the square root of 16 minus x squared, right? The plus would be the top half, and the minus would be the bottom half. Okay, this reinforces a point that hopefully was vigorously made over the last couple of years, and that is if you're solving a radical equation, if you take both sides of the equation to a power, and that's what we do, right? We isolate the radical and take both sides to whatever power we need to undo the radical. If I take both sides to an even power, remember that I introduce extraneous solutions, right? I change things. Is that all making sense? Right, so we'd have to, if I were starting off, this were different context, if I were trying to solve this equation, for example, let's say I had this is equal to, I don't know, let's say that was equal to 2, right? So I want to know when is the y value 2, which would be these two spots on the semicircle, right? If I were to square both sides, I'm likely to get extraneous solutions that shouldn't be there, right? So I always have to check all my solutions back in the original equation. Remember that stuff? We'll get more practice with that, as the year goes on. Calculus is kind of unique. We learned a lot of new calculus, but you also probably will do more algebra in this 1 year than you've done cumulatively in your whole life, just in this 1 year. And you get really good at algebra, because it just brings everything together. Okay, so anyway, that's, quick, brief review of how we get this thing. So then if we're trying to look at this semicircle on the interval from 0 to 4, including 0 but not 4, what's that going to look like? Well, from 0 to 4, that's just going to be this part right here, isn't it? Everybody agree? Okay, so then going back to our picture, that looks like, oops. So it looks like either that guy, or that guy, or that guy, right? This one we could cross out. And those are kind of small. You see what I'm saying, though? All of those have the correct behavior. They're including, they're portions of a semicircle where we're including x equals 0, but not x equals 4, right? So those all look good there. What about the rest of this? So we'd have to have a closed circle at x equals 4 on the line segment, right? We have a segment here with a y value of 4. So that would work right there, wouldn't it? So this is the only one that's going to match. See, this guy doesn't have that behavior. That should be closed and that should be open, shouldn't it? Right? So we get the idea. I mean, maybe I belabored that point too much, but this is the correct graph then. Okay? Everybody agree? Okay. And then at 8, x equals 8, it jumps up to the y value of 8. Okay? Hang on one sec. Okay, so then how are we going to say this domain? This is the part I wanted to get to. How are we going to say this domain then? Yeah. How would I say that domain? Which values? They want to know, and actually, specifically, I think they want to know where the limit. What are the domain and range of the function? At what point, see if any, does the limit exist? Okay. Left hand, I want you. We haven't really talked about that. I kind of screwed up on that one. I should have left that part out. A left hand and a right hand limit. I can tell you what they are. When we get there, I'll just give you a brief description. We'll talk more about it later. Okay, so what's going to be the domain then of this guy? It's defined everywhere, isn't it? Right? There's no place where the function is not defined, right? So the domain's going to be everything. Everybody see that? Right? The ant always has a place to stand somewhere when he walks from 0 up to 8. Okay, so that's the answer to part A. Where does the limit exist? Where's the limit defined? Easiest way to answer that is to find a handful of places, not even a handful, but the few places where the limit doesn't exist, and we'll just exclude those. Where doesn't the limit exist? Okay, it doesn't at 4, does it? Right? There's a problem because we've got a large break in the function, right? And at 8 it doesn't work because, not because the point is there, but because ants can't approach from both directions. Does that make sense? So you can't have a two-sided limit there. You can't have an ant approaching from both directions and agree where he thinks he's going to step, because the ant has nowhere to step to the right of 8. Same thing down here, right? An ant can approach 0 from the right, but not from the left. See what I'm saying? And so the answer to part B then, where does the limit exist? Well, it would have to be all values not including 0, greater than 0 and less than what? 4, because we can't include 4, right? So we'd have to do something like that, comma, or, it's an or statement, isn't it? Either the ant's going to be on this interval here, or he's going to be on the interval greater than 4 and less than 8. Make sense? Everybody see that? Okay, and then what about the left-handed and right-handed limit? Well, a left-handed limit just means you're approaching from the left. So where on this function could you approach only from the left and not from the right? At 8, right? So that's going to be the place where the left-handed limit exists, right? Only a left-handed limit exists. A right-handed limit would mean you can only approach from the right. So where's that going to be? Down here, right? That's going to fall under the topic of one-sided limits that we'll talk about real shortly. But we just haven't gotten to it in our textbook yet. I forgot that it was on that problem when I cited it. Okay? Does that make sense? So essentially, I'll give you the answer. Whoops. I'll give you the answer to these. I mean, you know them. At what point does only the left-handed limit exist? 8. X equals 8, right? And if they want the point, it's going to be at, what, 8, 4, I guess? Does that make sense? And then, at what point does only the right-hand limit exist? 0, 4. Okay. All right, make sense? Other questions? Any assignments?
How do you go from 2 and 3 up from 2?
Of the second assignment? Is that what this one is? Second one?
No, the first.
This first one? Okay. Okay. Okay, well, let's look at these. So is that, okay, so these are the ones, so this is kind of hokey. They want you to do it with a table, right? So, I mean, if you want to do it with analytically, now that you know how, I'm fine with that. But if we were going to do a table, how are we going to do a table on this one? Yeah, well, I mean, you could do, a table's a little different than a graph. A table would be technically something like this. If I pull up the calculator. Do you guys remember the steps for this? Grab your calculators real quick and just make sure you know how to do this, because this is a process you're going to do a lot throughout the year. All right, so if we want to take this function and we want to make a table of values surrounding -3, right? All we would do, you tell me, well, where would I go? Okay, I go to y equals to define the function. Good, so let me clear these guys out. And I'm going to have this function. Let's get fancy and use our fraction template. The shortcut to that, if you hit alpha on these calculators, you get, that's right. Yeah, there's 4 possible menus. If I hit like alpha F1, see, then you get these soft buttons down here that show you what each of those function buttons do. This is the fraction shortcut menu, function shortcut menu, matrix, and y variable. You'll use mainly 1 and 4, y variable and fraction. So if I just hit enter or 1, it gives me, you guys know about that, right? The fraction template, that's an easy way to get to it. And so then I would just have square root of 1 minus x. Hit the right arrow to get out of the radical, minus 2 over x plus 3, right? And so there's my function. I've defined it. Now where do I go?
Second graph.
I could look at the graph, but if we want to look at a table, I'm eventually going to go to second table, but first I'm going to go to table set. And I want it to start at, let's have it start at -3, right? We want to center it on -3. That'll start it on -3, but I can go up or down from there, right? So x is approaching a value of -3, so that's what's going to go there. What's our delta value going to be? I don't know. I mean, let's just make it 0.01 maybe, whatever you want. And now let's go second table. And if I scoot up a little bit, you can see here are the values approaching from both sides, -3, and you can see that to 2 decimal places, what are they converging on? Looks like -0.25, right? So there's our numerical way of getting that limit. Okay? Does that make sense? Now, why would you need to know that? Well, let's just say on the AP test, they threw one at you where you couldn't do it analytically. It was really hard. But they gave you access to a calculator or something. You can always do this, right? This is a technique that's always going to be somewhat effective on any function, right? Even if it's one that's really difficult to deal with otherwise. Okay? Make sense? The next one's pretty similar, isn't it?
Yeah.
Yeah.
I didn't know you were supposed to use like the table.
Okay, yeah. When they, and I guess here's maybe a point I can make about that. There are, if you think about what we did, there's really 3 ways to evaluate a limit. Graphically, which would be via you graph it on your calculator and trace along. Numerically, which is always going to mean with a table. And then the good way, which is analytically, which is where we spend the most time. Okay. So the one new thing I want to add today. So I'm gonna have you close up your Chromebooks for just a second here, and I'm gonna show you one quick thing that's really pretty cool. And then I'll let you work whatever time's left over, and I'll give you some work time tomorrow too. How's that? Let's take the limit of sine x over x as x approaches 0. If I try to evaluate that directly, what am I going to get? Now, what's sine 0? Do you guys remember? Yeah. Do you remember how to do how to use the? I'm a big unit circle guy. I think you can get everything out of the unit circle. No. Here, let's. If we look at the unit circle. Okay, all you got to remember, the unit circle tells you a ton of stuff. You can get so much mileage out of the unit circle if you use it right. If I take a point like just any random point on here that's got coordinates u and v, let's say x coordinate u and y coordinate v, well, that point defines an angle, theta, right? What are the values of sine and cosine in terms of u and v, right? All you have to do is draw a little triangle. Just draw a right triangle. This is a unit circle, so what's the hypotenuse in this case? If I draw this, if I drop down the altitude there and draw a right triangle? 1, right? Unit means 1. Okay? So it's got a radius of 1 or a hypotenuse of 1. And think about in terms of SOHCAHTOA, what is the definition of sine? Opposite over hypotenuse, right? So then think about that statement there. If sine theta equals opposite over hypotenuse, well, in terms of that point there, what's the length of the opposite side? If the coordinates of that point are over u and up v, v, right? So v over 1, but we don't even need the 1, right? Because it's unitary, it defines v as being sine theta, right? What's u going to be then? If I think in terms of cosine theta, isn't cosine adjacent over hypotenuse, right? So we could write this if we wanted to on the unit circle. We could rewrite that ordered pair as cosine theta, sine theta, right? Does that make sense? Okay. And while we're at it, I mean, there's just a lot of review. I'll just throw in review periodically when it makes sense. What about all the points on the unit circle, right? So then if we take each of the 3 principal angles between 0 and 90 degrees, between 0 and pi halves, what are they? So what are those important angles? We have one. 30. Okay, so we have one there at 30 degrees, which is what in terms of radians? pi over 6, good. And then in the middle it's at, okay, 45 or pi over 4. And then up here at 60 degrees or pi thirds, right? Okay, well, what are the coordinates of all those? There's a couple ways you can kind of internalize this, so you can do it really quickly. You know that, think about the numbers that show up in quadrant 1. You know that here the coordinates are going to be 1, 0. There they're going to be 0, 1. All the other internal coordinates are built from 3 numbers. They're built from the numbers the square root, or 1/2, square root of 2 over 2, and wouldn't you agree that has to be in increasing order? Right, because square root of 2 is bigger than 1 and square root of 3 is bigger than square root of 2. Okay, so you know that you always have big with small and in the middle with middle, right? So what's this one going to be? This is a big X value, so the coordinates there are going to be big X, small y, right? What are they going to be up here? Small y, big X. What are they in the middle? Middle, middle, right? Make sense? And you can do that in any quadrant by just reflecting those, by making the signs positive or negative, right? See what I'm saying? Okay? There's another trick for that. Put your left hand up. You know this trick? Oh, this is a great trick. Put your hand up. If you want to do this axis right here, for example, that's your thumb, right? So the x coordinate is always going to be above your thumb, or the top measurement, and the y coordinate is going to be the bottom measurement. So this is the x-axis. Whatever the number of fingers up here is, you're going to take the square root of that divided by 2 is going to be the value of the x coordinate. So what's the square root of 4? 2 over 2 is 1. How many fingers are below? 0. What's the square root of 0? 0 over 2 is 0. Let's move up to here. That's that finger, right? So the x coordinate is going to be the square root of 3 over 2, and the y coordinate is going to be the square root of 1 over 2. If I do this one, that's your middle finger, I get x coordinate square root of 2 over 2, y coordinate square root of 2 over 2. If I do this guy, I get the x coordinate is the square root of 1 over 2, so 1/2, y coordinate square root of 3 over 2. If I do this guy, x coordinate is 0, y coordinate is square root of 4 over 2. Pretty cool, huh? Right? You can always remember them that way too. All right? Why was I doing this? Oh yeah, okay, so we were just trying to, you were trying to tell me what this, if I directly substitute, what's that become then? So sine of 0 is right there. Sine's going to be the y coordinate, right? So 0, okay? Over 0. So it's indeterminate, not surprising, right? So what we want to do, our goal for today is just to come up with, to resolve that indeterminacy. Okay, and there's a great little proof. How much time do we have? I want to make sure I get through this. What we got here? Oh man, that's... I'm going to do it tomorrow. I don't want to get interrupted. This is so cool. This is really an interesting proof I want to show you. Okay, you just work today. We'll do it tomorrow. Yep. I'm sorry? Yeah, bring it up here. Yeah.